Music theory! Color wheel mapped to the pitch wheel. And don't worry, although it kind of looks like it at first, it's not woke and therefore will not make you go broke. Quite the opposite, providing insights, helping you understand music theory in general and create tools such as a color-based fretboard, allowing you to better visualize, map out, unlock the fretboard. Our overall objective, to have a very practical, functional color system used to help recognize musical patterns, one so detailed that we can actually name the musical patterns and what we're doing with the color system itself. To do that, we need a color system to give us the points that we're working on as well as the distance. The points are typically named in the 12 notes of the musical alphabet, or the Nashville number systems, the modal points, and then the distance is usually the intervals. If we have absolute colors for those two things, we can name a movement from one note to another note through simply the color system as we move from a note point or nodal point or modal point to the next place, distance-wise being the interval. To do that, we want to be able to understand what sound is, how we can visualize sound as either like a note number line or a circle, or more specifically, a spiral staircase that has repetition as well as an infinite increase and decrease, and then how color works and how we can map that to have the same shape so that we can give a one-to-one relationship, providing thus those absolute colors that we desire so that we can build the association. All right, first, sound has a natural cycle built into it called an octave. So we've discussed this in a prior course or section, in that when we measure sound, it repeats to us in our ear. So that means any culture in the world has got to come up with some system that has that repetition. Otherwise, men and women would not be able to basically sing together because our voices are typically at least an octave different. So that means whatever system we come up with has to have that quality to it, which we can visualize as, in essence, a circle. So for example, the typical example being in the middle of, say, a piano, we're not looking at C, we're looking at the A. The start of the alphabet is measured at 440 hertz. That's going to be the measure of the wavelengths, right? And that goes up to 880, would be an octave up. It would be another A, an octave up. You can see it as a note number line because it's going to be higher, but it also has that quality of kind of a repetitive motion. So we can think of pitch as a note. It's going to be a number line. So in other words, when we start to visualize what is happening with music, we could think of it as a number line going infinitely up or to the right, infinitely back, or to the left, and it does function that way. However, because of that octave quality, we can also think of it kind of like a circle going around a lap. Now this is more of an oval, but a circle, the fact that it repeats is what we're getting at here, meaning that although it still goes infinitely up and infinitely back, it still has a quality of repetition that we want to take into consideration. Therefore, the actual shape that we would like to be able to visualize is more like a spiral staircase. Why? Because a spiral staircase, you can still see the repetition. You can say one right above the other. Those could be like two A's, but one's going to be an octave higher, meaning you still have distance. Now, we can't really visualize a spiral staircase when we're trying to work on something. We can kind of see it. Oh, I get it. It's a spiral staircase. But if I'm trying to work and say, how far away is this note to that note? I'm either going to be thinking in terms of a note number line or like a clock that's going to be basically repetitive, always knowing in the back of my mind that there's actually both of those qualities that are happening. Now, color is a little bit different, although similar. Color, in contrast, is a continuous spectrum of light wavelength. So this is basically all of light, right? And our eyes can pick up some component of the light wavelengths. So this is the visible light that we're going to basically be working with. So obviously we want to take that visible light and then break it out so that we can get a very systematic color system that we can apply to our 12 note system. So obviously this is the range of light that we have to be working in then. Now, when we think about light, they measure it similar in that we actually have a measurement, an actual unit of measure that creates, in essence, the light. And it's usually going to go from the shorter length of light to the longer length of light. So, and that usually goes from this like purple color on the shorter lengths up to this red color to the longer lengths. So this is the actual spectrum of light that we have. Now notice as the wavelengths get longer, it's not like you get this repetitive quality. It doesn't go back to purple up here or like a darker purple or something like that, which is what happens with pitch. With pitch, as we saw, a 440 wavelengths, if I keep on measuring the wavelengths and they go up and they double to 880, then we have that octave. That's where you get the spiral staircase. It's not here with color. We don't have that. It's not there. Not only that, but you can imagine if I try to bend this into a circle, what's going to happen is the red is going to be at like 11 o'clock, and then it's going to blend into this purple over here. And that's a harsh blend, right? That doesn't look quite right. It doesn't seem like it's going back on itself. We don't have that circular quality that we have in music. But painters and whatnot will want to do that. They're going to want to add that quality in. And oftentimes they actually flip this around. So they'll flip it around this way and have the longer wavelengths first, which is red, and then move down to the shorter. Why would that make sense? Possibly because in our realm of being as human beings, and the light is kind of similar to temperature, I think of it in some ways. And we live in a temperature area where the red is more of a warm color, and then when you go this way, it gets kind of like cooler. Even though if you're talking about like fire for heat, you know, the blue is actually hotter, right? But in our normal everyday human experience, I think it's like warm is red, warm is like hot red, and then it's getting cooler as you go this way. Even though again, if you talked about a flame, then it might be right. So we have this problem of when I try to map the color wheel onto the pitch wheel, one, that it's a spectrum, two, even if I can bend it into a circle, it doesn't fit right. There's a gap between the red and the purple over here. And three, artists like to flip it around so that the red is first. So when they make a color wheel, they typically start with red. All right, keeping that in mind, there's no natural repetition. However, artists, okay, so measuring sound. So how do we measure sound? We've talked a bit about this in a prior course or section, so won't put a lot of time on it, but pitch is measured in hertz, vibrations per second. So basically we can actually measure the vibrations, how many vibrations are happening per second. And then as we measure more vibrations, you can imagine in theory, like a note number line, a vibrations number line, it goes up infinitely and back infinitely. So we can measure it thusly. So color is measured in nanometers, So the length of light waves. So both of them have the quality of measurement. They have different things that we're measuring them by, of course, the number of oscillations for sound or compression waves, however you want to think of it, and for light, the length of the waves. So they're both phenomenons that are similar in that way. We can scientifically measure them. They both result in a spectrum, although the color does not have, once again, this circular quality. Notice what has happened here is we bent it into the circular quality, and this is what we call, in essence, the color wheel that we're going to come up with. So if sound can be put into a circle, then we can also put color into a circle. Now you might say, well, you just put it into a circle. What does that mean? Well, we'll do this mathematically in our projects just to show you how it works, how in essence you derive the 12 notes in the musical alphabet. But in essence, if you think about 440 to 880, that's the distance of the octave. And then what I'd like to do is convert that distance into equal measurements of 360. And you can use like a formula to do that. It's kind of a log idea in order to do that, in order to convert it into a circle. And the reason I want to get it into a 360 degrees, you could just get 12 points that are around the circle, but I'd like to map out, and we will do so in our practice problem, 360 degrees. Why? Because if I wanted to get technical and say, well, what if I was playing like an A, but I bent the string up a bit? Then I might not get to like an A sharp. I might be in between somewhere. And so you might want to look that up on the 360 circle, which you can then map out or tie to the color circle. Now, so that's what we'll do. So color, you can do the same thing. It's also a spectrum. So we can basically map it out and say whatever the wavelength, whatever the lengths are from the nanometers, whatever they are, I want to fit it into equal units of 360. Because if I have 360, that maps onto 360 degrees, allowing me to map it onto a circle. So I would like to have, what we're going to do is line these two things up side by side. Color, wavelengths mapped in hertz, color mapped in nanometers, but then standardize each of those measurements so that we're looking at equal distances of 360 degrees, therefore being able to map it onto a circle. Once we map it onto a circle, we can basically treat it like a clock. We can choose 12 equally distanced points on the circle, which will give us the equivalent hertz versus the equivalent amount on the color wheel, which would be 30, 60, 90, 120, 150, 180, 210, and so on. So we can, and that's going to be the letters that we basically are going to be applying. So these numbers over here do not represent hertz. They do not represent nanometers. They represent the relative position if I convert these two distances to a 360, an evenly spaced 360 degree distance, right? And then I can map it onto the circle. That might sound a little wonky, but we actually will work that out if you want to look at the detail, but that's the idea. So sound divide octaves into 12 equal spaces, points, notes, and color divide color wheel into 12 equally spaced hues. So then I just name these 12 points. That's in essence how they derive the 12 notes in the musical alphabet. Okay, so mapping the pitch circle to the color circle. So each note, so once we have this mapped out, then I can derive an exact color, and we'll use help from like a ChatGPT and our color system to do this. Now note, we kind of cheat a little bit here because as we saw, the color spectrum should be going, you would think, from the purplish color to the red, and we basically, as artists, the artists make it go the other way. So we start with longer wavelengths and then we go to the shorter wavelengths. So you can see we're going from longer wavelengths are red, and then it's going around the circle. We bent it into a circle. That's what you would expect. It's just going from longer to shorter. And then over here you might say, whoa, what happened right here? That wasn't on the spectrum. This bit wasn't on the spectrum because we started with a sharp purple and then it went to red. So you would think if you bent the thing into a circle, you should have the purple right adjunct or at 11 o'clock going into red. But that doesn't blend well, right? So what do the color people want to do? What do the artists want to do? They come up with a mixed color that's not actually being measured by light. So what happened here? From a scientific perspective, we can measure light from short wavelengths to long wavelengths, and then it's just a spectrum. And if you could bend it into a wheel, but you'd have this basic thing, this jarring thing of it going from purple to red. So the artists said, no, we like in our human realm it to go from warm to cool, and we see purple as cool, even though a purple flame is hotter than a red flame. But in human realm, we think about color and what we draw from warm to cool. I think that's basically what happened, right? And I don't want this jarring thing going back. So I don't care from a painter's standpoint. that this doesn't fit the wavelength of light, I'm going to come up with a color that's going to be a mixture of colors, blending it together, so I have a nice blend that goes back to the red. Okay, so that doesn't map on scientifically, mathematically perfectly for our analogy. However, as a metaphor, that's perfect. That's exactly what we want. Why? Because that actually mirrors exactly what pitch does, right? Because the pitch, as the pitch goes around the circle, if this was going A all the way around and going to an octave, and then we're going an octave up, it does, the pitch does repeat itself. So that means we do want, so the color doing that is perfect. That's exactly what we want. It's not exactly scientifically one-to-one mathematically proper. The painter fudged it, flipped it, mirrored it, and then added magenta. But from analogy standpoint, that's perfect. So this color wheel, what we'll do is we'll kind of show you how mathematically we do that in our practice problems. But then we're just going to use the color that's given to us in the color wheel, which is measured by HAS. There's a color system. I forgot what it is exactly, but they already have it mapped out. And that color system has these colors, which are the hues, mapped out to a 360-degree circle already. So it's already done for us, and they've already kind of made this. So we'll actually use that color wheel. Now the problem is, like Excel doesn't use that color system. They typically use an HEX color system. So that's not perfect because that color system takes into account multiple dimensions, not just hue mapped out on a 360-degree wheel, but also things like brightness and lightness and what do they call it, saturation and whatnot. So they give us these numbers that take into account all these different factors, and therefore the numbers do not map onto a 360 wheel. But what we can do, of course, is simply convert from a 360 color wheel using AI. Just ask AI, I'm looking for this 360 degree color, 60, convert it to the HEX color system. So we'll do that in our practice problem, and then you can derive the color, and we get an absolute color system which maps out perfectly, and then we can get the names of the colors. Now note that these names are somewhat, you can think of maybe arbitrary. I mean, red is red, that's not a problem there. But when you get to like yellow green, then there's a question just artistically, what would you call that? The actual color number should be somewhat exactly what it is, right? Because we got that from a 90 degree on the color wheel and then converted it. But the actual name is going to get muddy when you're looking at colors that are closer together. Now you also might say, well, look, these two colors are pretty close. I'm not sure if my eye can pick that apart. And some people's eyes are better than others, just like some people's ears are better than others. But I do think you can get better at it, right? So meaning just like your ears can get better at picking up pitch, your eyes can get better at distinguishing shades of different colors. So I thought that at first, and then I was like, dude, what? You could totally do that, right? Like, I mean, I could see the difference between those colors if I look at it, particularly if I'm only working with the 12 colors here. Now, we're also going to give an absolute name to the colors. I want to memorize the names. So these names become important. Why? Because then I can name, if I'm going from the A note to the B note, I can name that just by color. I'm going from red to yellow, going from the red note to the yellow note. That means A to B. It's not like it's an abstract, arbitrary thing, because red is A, right? And then, okay. Now, one other thing just to note here, you might say, well, you should have started the spectrum on C, because the piano typically starts on C, even though we measure the spectrum from A. We'll discuss that more later. I think the reason I start on A is because I think it's more logically consistent to start on A, because that's where we start the musical alphabet, and that's what most people think of as 440 is the number that comes to most people's minds if they know any number in hertz more than the number for C. So I just think that it makes more sense logically. There's a lot of things on the piano that don't make exact sense musically. I mean, in terms of if it wasn't for the piano, we probably would do it differently, right? And so again, you can debate that, but that's why I chose to start the spectrum from A. Now notice if you can visualize the color wheel, that also gives you a visual idea of where you are, like where, right? Because I can see the distance basically with the color wheel. Okay, so also what we want to do then is see the notes. I want to be able to say red is A, and I want to say A is red. Flashcard time. I want to say spring green is D, and D is spring green. D sharp or E flat is cayenne. Cayenne is D sharp or E flat. All right, so I'd like to do that, and then it's often more practical even to do like a Nashville number system with the colors, because if you've seen our prior course or section, we've talked about an analogy of we're always working in a 7-note collection generally in Western music. There are 12 sets of 7-note collections, right? 12 7-note collections that we're working in. So the Nashville number system is a way of giving us an absolute number from the perspective of a number for all of the 12 sets of 7 notes. Similarly, we might want to do that with color. In other words, I'm going to take the C this time. Why am I taking C and not A? Because this is an area where I think most people work, right? They work from the C as our practice because it doesn't have any sharps and flats in it, and it's easier to work from. So I'm just going to take that as we do with the Nashville number system, or in a similar fashion at least, and look at the colors related to the key of C if I apply the formula out, meaning C, whole, whole, half, whole, and then it goes back here, whole, half, meaning all the ones that aren't sharps and flats if I start from the key of C. And so that's going to give us this set of colors. Now, if I use that set of colors to name not the notes, but the points of the nodes, the Ionian or Nashville number system, the Dorian, the Phrygian, the Lydian, the Mixolydian, the Aeolian, the Locrian, and I memorize just these 7 colors for what I would call the continents in our color system, those will be the same for all 12 collections of 7 notes, allowing us to visualize the pattern as we move through all 12 sets of collection. I'll show you in a second. So this builds a 1-to-1 map of the 12 notes scale into 12 hues. All right, so this is our fretboard. Now on the fretboard, we're only looking at the points right now. We're not looking at distance. We're not looking at intervals, in other words, or modal distances. We'll talk about that later. But we're just looking at the points. You can visualize the points 2 different ways. One is the letter point. It's an A. This is a B. This is a C. The other is the relative position in the collection of notes that we're working in. In this case, we're looking at the 7-note collection for the key of C major, meaning we're looking at the Ionian is a C, which is Nashville number system 1. The Dorian, which is this D, is the 2, or Nashville number system 2. The Phrygian is here. That's going to be sky blue, and so on. So if you look at it that way, that's often the most functional way to look at it. So we're tying the colors in this case to not the note points, but the relative nodal points. Why? Because then if I move forward to the collection of notes, the Ionian is now the C sharp or D flat. You can see this pattern, which I call pattern number 1, or from a caged system, you might call it a G-shaped C major type of pattern. And sometimes you would add this one here, but I want to just keep it simple with these collection of notes right here. And you can see it moves up. Now it still looks quite busy. You're going to say, well, there's a lot of color there. It might kind of throw you off because there's a lot of brightness going at you and you're not used to it. But once you get used to it, it's quite helpful, because now I can see all of the relative positions have moved up, right? I can see this pattern and I can associate all of the relative positions, which is really the important thing we want to do. I can say, well, I'm going from the Aeolian to the Phrygian is from a Nashville number system, the 6 to the 3. I still have the pattern of going from the 6 to the 3. It's going from the red to the sky blue, red to the sky blue. So all of the patterns, like with the Nashville number system, can be assigned by color, and you can see them move through. So now I can move up. This is just like I say, the fretboard is like the planet rotating around in a circle, And all the continents on the planets didn't move. We're just looking at it from a different perspective, right? So now they're here. Now they've moved up here. So this is the A. Now that it was the A sharp or B flat. Now the B is the Aeolian, and all of the relative positions moved up. All of the relative colors move up. Now we've moved up to the B. So now the Aeolian is on B. Here's the Ionian on D. We're on the 7-note collection now around the D major. And so and down here we moved up to D sharp or E flat, and then here now we've moved up to the E, and you can see the pattern moving across. Now you could keep on continuing the fretboard out here, or the fretboard wraps around. So now you can see the pattern wrapping around here, and here's the open position, and now we're in the 7-note collection around F major. Now we're in the 7-note collection around the F sharp. Now notice that this fret 0 is the same as fret 12. So you have a repeat fret here. So it looks like it's a little bit longer because of that repeat. You could have stopped it at 11 and then you'd have the same distance. But then there it rolls through, right? So that is really a useful tool. So representing octaves lightness. Now you might say, well, what about the fact that there are octaves? So I could map everything out the way we have it now, so that we can look at the local distances, meaning here we mapped out the entire fretboard with all of the notes that are the same, or the relative points are the same, as though we're just going around a circle. So in that case, we're visualizing everything like we're going around a track, instead of like a note number line, right? So what if I wanted to add the dimension of octaves using a color system? Now, we can't naturally do it with color because we said that color doesn't have that repetitive quality as the length of the light gets longer. It's not like it repeats on itself the way it does with hertz, with pitch, but we can still do something. Since pitch repeats at higher frequencies, we simulate this in color by adjusting lightness. So in other words, this color over here, these numbers are just really dealing with hue. Hue represents the actual color. We also have different factors that don't relate really to the measurement of the length of the light, but do have a strong impact on our eye. Those include things like brightness, lightness, saturation. So then I can adjust those things. So this one, I set the lightness at what 0.5 I believe it is, which gives us the brightest or the most pop for that hue. And then I can say, okay, well, what if I go down an octave, right? So what if I go from, I'm in the middle of the piano, like 440 hertz A, not the middle C, but the A, to the upper A, to 880 A. And if I go higher than that, I can keep it at red, but now I'm gonna say the lightness is now lighter. So I'm gonna make it a shade lighter. So that means I can map out, it's a lot more complicated to do, but we can do it on a fretboard in Excel and say, well, look, if it's an octave higher, we're going to make it a lighter color. And if it's an octave higher than that, we'll make it even a lighter color. And if it goes down an octave lower, we'll make it a darker color, an octave lower, a darker color. So all of these will be named red, but now I can say it's a red 1 shade lighter, which means it's higher up in pitch. It's an octave up, or red 2 shades lighter, or red 1 shade down, and so on. So this gives us color kind of a 3D. So what does that do with color? It gives us that dimension that we don't have with just hue. It pops it off the page for us. Now it doesn't work exactly the same though, because it's not like I can measure the hertz and map it on with the same 360 color wheel, but I can just say, hey, look, if it's an octave higher, we're just gonna map on the same thing and then change the lightness. So that would give you a fretboard that looks something like this, right? So now I'm just showing you the note number and the note name, and you could see like this A is what we would say in the middle of the piano, the 440, for example, and then this A is note number 13, meaning if this is 1, this is 13, because we're measuring from the middle of the piano. 13 minus 12 is 1, or in other words, it's the A, or the 1A plus 12, an octave up. And it's still red, but it's going to be a shade lighter. This one is still red, but it's going to be a shade lighter. And then And then on the fretboard, normally we don't go too much back further than in the middle area that's on the piano. But if you're on a piano, then the shade darker is going to be important here. So here's a G, here's like middle G, right? And then here's a G that's going to be a shade darker, and that helps you to visualize the pattern, but also get the octaves in there. Something that we can do in a similar way when we measure distance, which allows you to, particularly on a fretboard, practice chords and think about whether they are inverted or not, something many people don't really take into consideration as in-depthly as you would on like a piano, where it's more clear if something is inverted or not. So intervals as rotations. So a musical interval is a movement from one note to another. So now that we have the notes, we've got 12 notes. If I want to name what I'm doing musically, I not just need notes or points, modal points or notes. I also need distance, intervals, to say how far I'm going. So on the color wheel, this becomes a rotation from one hue to another. So for example, red to yellow is a major third. So each interval equals a consistent color jump. So in other words, I could look at obviously the distance between any of the colors, because the notes are fixed, will give you an absolute distance. Meaning if I go from A to B, that's a whole step away, or it's going to be a 2-note away major second, if you want to call it that as well. So I could say red to yellow is always going to be a 2-note away major second. So that's great. Now I was playing with the idea of being able to say, well, what I should do is take the average of the A, like 440, and the average of whatever the B is in hertz, and or the log average possibly, and take the average, find it on the color wheel, and then get the color, which would be really cool mathematically. I actually mapped it out, and it's pretty cool to do, because then you could get the average color for anything that you're playing, right? And I could do that even with chords. I can say, okay, let me map out the average in hertz of all the chords, even taking into account octaves and whatnot, and get the average color. In other words, you could even say, well, 440 to 880, I can add those two and divide by 2, or take the log average to put it on a circle or whatever, and say what the average color would be. So that's great, and it was cool to do, but I don't think it's the most efficient way to come up with a distance mapping system, meaning I'd like a whole nother system for all of the distances that we can have between the 12 notes. I don't want those distances to be too close. I want them as spaced out as I can from the colors that we already have, right? So how could we do that? So we could just take the color wheel, see how this is 30, 60, 90, whatever, and just rotate it 15 degrees. So that now I'm just going to take the same distances. There are, in essence, 12 distances if there's 12 notes, if you include not going anywhere, like from the Ionian to the Ionian or A to A. And then if I rotate everything 15 degrees, I get another set of 12 colors that are pretty close or approximate, but I get the same idea of them being as spaced out as they can, both from these color sets as from themselves, so that we have somewhat. Again, it's not as mathematically pleasing, but I think it's the most efficient way to have a whole nother color set that I can apply to just the distance, allowing us to name the point as well as the distance with color. So this might not be as useful as I think the Nashville number system is in color, but I still think it's a really cool thing, and it could be quite useful. So now I notice if I start on not going anywhere, that's going to be, I'm going to call it flame now. 1 is amber, 2 is chartreuse, 3 is lime, 4 is mint, and so on and so forth. So we have these colors representing the distance when I don't go anywhere, when I go 1 step up, which could be a half step, or a 1 note away minor second, when I go 2 steps up, which could be a whole step or 2 half steps, or a 2 note away major second, 3 notes up, which would be a 3 note away major third, 4 notes up, 4 note away, this would be a minor third, 4 notes would be a major third, 5 notes would be a perfect fourth, 6 notes, possibly a diminished fifth, 7 notes, a perfect fifth, and so on and so forth. I don't care what you call it, 7 notes up or a perfect fifth or whatever, I'm going to call it azure for the color. So that means I can then look at distance-wise and say, well, if I'm going from A to B, I can name it all with color. I went from the red note to the yellow note, which is a distance of chartreuse. Now that might seem very abstract to say. I went from A note to A sharp, and the distance is amber. Again, that might sound kind of weird to say. I get it, kind of wonky, kind of like, but that also means that when I map out the fretboard, you can see everything by color in a similar fashion as we have over here. And I find that if you actually name the colors, it helps you to visualize it a lot better as well. So for example, here's a fretboard where now I have both. Here's the frets. I'm in the middle of the fretboard, 5, 6, 7, and 8. They have two sides to them now, meaning the first side is giving me the point measured in note name, A, and the relative position from a Nashville number system, the 6th, and the node name, A, for Aeolian. This one we're going to say is, and this is going to be the distance. So this is going to be the distance from a particular node, in this case being from the key of C. Let's look over here at the Ionian. This Ionian, this is the 7-note collection around the C major mapped out, giving us the point and then giving us the distance. So from the perspective of the C major, the C is the 4th note if I make A1, 1, 2, 3, 4, and then it's the Ionian node if we're seeing it from the 7-note collection around the C major. We applied the formula to C major, whole, half, and so on. And it's going to be 1 from a Nashville number system. Now, if I don't move anywhere, what's the distance from C to itself? It's a perfect first, or we went nowhere. It's a 0 note away from the Ionian node, 0th modal half step. What if I look at this C, for example, still 0 note away, a perfect first. What if I go from this C to this D? Well, that's going 1, 2 notes up, or 2 half steps. You could call that a major second or something, right? So now from there, I could say that I'm going from C to D. This is C to D, which is a distance of you might call it a major second. So a major second. But you can also call it by color. We're going from yellow green to spring green, and it's going to be going a distance of chartreuse, I believe is the distance here. Now again, that might seem kind of wonky, but you can also see the distances color-wise, and you can actually map out the fretboard with just the distances if you want to, which can help you to map out the interval distances. I'm experimenting with multiple color systems on the fretboard, which again looks very busy, but it allows you to name everything quite specifically on the fretboard. Now this is the same collection of notes that is the 7-note collection around the key of C, but I can pivot the second dimension to be around any perspective of the 7 notes. In other words, instead of measuring it or looking at it from the perspective of the Ionian, we're now looking at it from the perspective of the Dorian node. So the Dorian is now the perfect first, 0 notes away, or flame color. And if I go from the Dorian to the Phrygian, or from the D to the E, that's a distance of 1, 2 half steps, which would be a major second, and that's the one which is now chartreuse from the perspective of the Dorian, right? It's different than up here. So that is something that should be easily able to do. Not easy really in Excel, might be easy in a database program, but I map that out in Excel, and I find it to be very useful in my practice. Anyways, so why this matters for learning. So I really think it's just good to learn like music. I think this will be helpful to anyone to practice, but I really think that these types of things is just perfect for children to learn with, right? Music shouldn't be a separate subject in grade school. Music should be integrated, in my mind, to learning math, and then learning intervals, learning basic counting, maps. Basically, we're looking at a map of the territory, spatial visualization, patterns. There's nothing better than music, and then going from there to spreadsheets and computer programming there's nothing better than the logic of music to do that if we map it out as logically as possible. Not only that, but we can compare and contrast the measurement of music, how the phenomenon works, by comparing it, mapping it onto the way color works to give us a compare and contrast there as well. So children can see music like a rainbow. So we have the pitch and is the hue. And again, whenever I say rainbow, I feel like I'm being political and stuff. You know, it's the spectrum. So we need to me, we need to depoliticize color, right? And start to say it's okay to look at color scientifically here. It's a scientific thing, phenomenon, and we want to pitch it out. We want to measure it, and then I want to compare and contrast that phenomenon to that of sound. So pitch is going to be equivalent to the hue, color, which we can map onto each other, and then the octaves are going to be lightness, meaning I can add another dimension of lightness, popping it off the page, and then the intervals equal rotation. So this helps reinforce math, circular learning, frequency, doubling. All of these things are just basic things that there's no, again, should be just normal curriculum, and there's no better practical thing to work with than music. Really, I mean, seriously, like, I'm an accountant, and accounting is not as good as music to make an Excel worksheet with. Music is at least as good as debits and credits to make an Excel worksheet. So clarify music structure visually, and create color-coded instruments or sheet music. And again, whenever I say color-coded, I feel like there's some kind of, just because of the political environment I happen to be in California in the United States, I feel like there's some kind of political thing there. It's like, no, the colors are coded to define the notes, right? The notes, they should be given, you should be able to visualize the notes by color. And again, someone that works in spreadsheets and numbers, that's really helpful. If I can visualize whatever I'm looking at and look for the color, if I can get to the point where I actually can see color on the fretboard because I've got it so in my mind, right? That's where I think you could get it, particularly if you're young and people and colors being presented properly to be used for proper associations. So final thought, the pitch wheel and color wheel may not be identical, but they are mathematically analogous, and that's more than enough to make this a revolutionary way to teach music and science together. So again, I just want to point out, final thought here, that you will see stuff out there that says like, well, color is the exact same thing as pitch, and it's a one-to-one relationship, and they're in the same phenomenon that we're taking almost like a spiritual thing as well, and which has some truth to it, a lot of truth maybe, but then they take it too far, right? And so we have to watch out for that kind of thing too. How do you do that? Well, you break it down more systematically so we actually know what's going on, right? So if you compare and contrast the two phenomena, then the better you could do that, the less likely you're going to get into these wonky kind of things that kind of take things too far in whatever direction they're going in for whatever reason they're going that direction.